In this lesson, we're going to be looking at how we can create this type of thing. We're going to be doing some stuff with vellum wires and attaching it to, of course, the mocap dancer, because it wouldn't be a true Houdini for motion designers course if we didn't have some sort of Method Studios inspired mocap dancer with physics attached to it. So we're going to do the whole setup. We're going to bring in some mocap data, and then we're going to sort of fill it up with a bunch of spheres, and then we're going to do this dancing sim until this point where it gets we do this little backflip, and then it's going to break apart into a bunch of individual pieces. All the while, then once we're done with that, we're going to feed it into this vellum sim and attach a bunch of wires to it that all break away and fall apart as the mocap does its thing. So I think it's a pretty fun lesson. There's lots of little elements. We get to sort of start doing things where we're combining different areas of Houdini together. We've got rigid bodies and vellum all together at once. So it's going to be fun, and let's get to it. First thing, we want to start off in our project called Lesson 09D Vellum Dancer Start version 1. And here I've just placed a room and a camera that I've already matched up with the animation that I'm going to be bringing in from Mixamo. So at this point, what we want to do is create a little some geometry to hold where our animation will be going. So let's just throw it on a geo, and I'm going to name it animation. So in here, if you want to follow along, I'm going to be doing all of my settings and stuff specifically tailored to a certain piece of geo and a certain animation in Mixamo. But if you don't have access to Mixamo and you want to follow along, you can try to follow along using maybe test geometry crag here. So if you hit the tab key and start typing in crag, you'll find this test geometry, and basically it's just this creature that let me just turn off wireframe mode, and let's say hide other objects real quick. So this test geometry is just this sort of rock creature that walks through, has a sledgehammer and picks it up, swings it around, smashes down. Maybe if we go a little bit further, boom, smashes his hammer down. So you could follow along with this geometry, or you could follow along with the Mixamo geometry that I'll be using of a breakdancer. So this is a message from the future. As I go through the beginning parts of this tutorial and I'm following along using the mocap dancer data that I'm about to import in, I didn't test this test geometry to see if it would fit in the setup until much later. So I just, in order for you, if you're hoping to follow along using just the test geometry, just wanted to quickly insert a little bit of a sort of a correction here so that we can get the test geometry to work with our simulation. So to do that, one thing that is going on is that this geometry is packed currently. If I middle mouse here, you can see that it's just 67 points, prims, vertices, and packed geos. So what we need to do is actually convert this. So if we throw it on a convert node like this and wire it in, you can now middle mouse click and you can see we get all of our points, primitives, vertices, polygons, etc. Everything is all unpacked and ready to go. So if I now show smooth wire shaded, you can see that we've got this nice dense geometry on our animation right here, except this hammer is this hammer is not as dense. And this normally wouldn't be a problem, except we're going to be using this mesh as a cage deformer sort of thingy, using the point deform node later on. And in order for it to work, we're actually going to be scattering little spheres inside of this hammer handle. And in order to deform those spheres appropriately, they need to have close by reference points for which they are supposed to be moving. And the problem that we have right now is that at certain points in this animation, this hammer, the center of this hammer is actually closer to the hand, this forearm, than it is to the hammer handle itself. So what we need to do is actually add some additional resolution to make this a good candidate for point deformation later on down the road. So let's just quickly do that. And the way I'm going to do it is I'm actually going to go back up here to the test geometry. If we look at our geometry spreadsheet, and we middle mouse click here, you see we've got this name attribute. If I go over to my primitives, I've got these names. If I sort this name, you can see I've got a hammer name right here. So we can just split off the hammer and do a little bit of work on that and then recombine it with our original mesh. So let's throw down a split. And I'm going to just wire that in here. And this is right after the test geometry and before we unpack it, because these packed prims are what has the name. I'm going to go in the split group section and I'm going to find the hammer, which is right there at the bottom. So now we've split off the hammer and made it its own thing. And then we have the rest of our geo over here. I'm just going to alt drag this convert over so that it is separate into this other stream over here. So we have now converted this geometry separately, and we also have this geometry. So to change the resolution of this, I'm just going to remesh it. So let's run on remesh node like this, and let's just bring the target edge length down so that it's adhering to its original shape. We're going to eventually be filling this with spheres, so it doesn't need to be super accurate, but for right now, something like this should do. And the problem here now is that because this geometry topology is changing, it's actually going to get a different remeshing result every frame. You can see those polys are kind of jumping around as the mesh moves through space. It's having to recalculate how it's remeshing this geometry on every frame, and we need consistent topology, so that isn't going to work. So we're actually going to throw in a point deform here to point deform this based off of the original geometry. So to do that, we're going to throw it on a point deform node, and we're going to wire in the first thing we're going to wire in is going to be this remesh. But the problem is we want to actually time shift this remesh so that it is sticking only to this first frame like this. So if I throw it on a time shift node right here, we can stop this remesh on frame 1 by right clicking up here in the frame parameter of the time shift and saying delete channels. So now when we scrub the timeline, this hammer doesn't do anything, but this hammer kind of travels off on its own. So we can use the movement of this hammer alone to influence this remeshed mesh. So I'm going to put the mesh that we wanted to form in, which is this remesh. So we wanted to form the remesh. The second input is the rest point lattice. We actually want to take this is the rest point lattice right here. This is the one that isn't moving. So we're going to wire this one into the second one. And then in the third input, we can take the deformed point lattice, which is this. So we've got a hammer that isn't moving, and we've remeshed that, staying still every frame. And then we've got a mesh that's moving. And now when we apply this, we get our remeshed hammer, and it is keeping a consistent topology while following the position of that original hammer movement, which is what we're after. And then now we can simply just merge these two together to get a nice dense mesh that we can use for point deformation later on down the road. So if you have a Mixamo account, and likely you do if you have an Adobe account, when you log in, you get to a place like this. If you navigate to the characters tab, the character I've chosen is this Lola B. Stiperek. So you click on, you can see her, she's got some nice lettering on her clothes, and it's just orange with a gigantic zipper down the middle, which is cool. In the end, it's not really going to matter so much, but I thought this person looked cool, so I went with it. The next thing is in animation. We're going to want to use the breakdance freezes, and I don't really know a great way to search for this or to find the exact animation other than to go to freezes like so, and then it's going to be let's see, it's one that ends with a flip. So I'm looking for a flip. Maybe I just search for, yeah, no, it's this. It looks like it's this first one. So I'm going to just, if I look at it, it says breakdance freezes, description, breakdance freeze, combo. I don't know. At any rate, if we watch we watch the animation back, we get sort of this, you know, getting ready, doing a handstand, couple moves, one arm, and then a backflip. So that's the one that we want. So hopefully you're able to find that one, because I don't think I'm able to distribute Mixamo animations with my tutorial, but so that's kind of how you find that. So then you're going to click download. In my case, we're going to do, we want to do 24 frames a second with skin, keyframe, no keyframe reduction in an FBX format, which is good. So click download. And that will download, and I'm going to I'm going to copy this to my clipboard. So now, in my project, I have created a geo folder. I'm just going to navigate into there, and I'm going to paste in the FBX file that we just downloaded of these breakdance freezes. So now we want to merge this into our scene, and it isn't the same as the way we normally would bring things in using a file node. We're actually going to go up here to the file menu and use import Filmbox FBX. And I'm going to just leave all this stuff the way it currently is, and go and select. I'm going to go to my HIP file. I'm going to go into the geo folder. So I'm using this $HIP token, which basically is navigate to the area that this file is located. Then I'm going to go into the geo and select breakdance freezes FBX and hit accept and hit import. You can see that it creates this little subnet for us that has all of our rig and everything like that. But the issue now, if we, I'm just going to hide all this other stuff. If we click on this and hit spacebar F, first off, our animation is gigantic, but it is animating, which is cool. It's brought in all the, it looks like it's brought in some basic textures and a bone rig for us. And what we actually want is to get this down to size, but there's another thing, and you may have noticed, is look at all this. This is this tan color. What is all that about? And what is this thing up here? We've got takes activated. And you can see right here that there's all sorts of stuff going on. We're no longer working in our main take. If you're familiar with working in takes from cinema, basically anything that happens inside of a take needs to be handled with an override, and it can get really confusing really quickly if you aren't really familiar with that workflow, or you're not wanting to use that workflow. So I, in this case, don't want to use this workflow. So you might think, oh, well, I can just switch to my main take. So you can switch to your main take by either going from, you know, where it would be on this mixamo.com take. You can click the main take up here, or you can select from this drop down in the upper right hand corner, select different takes. So it looks like take 001 doesn't have anything, but when you go to Mixamo, that's where the actual animation occurs. Back up here on the main take, there's no animation, but I want to get this animation onto the main take. So, here previously, what I might have done is I probably would have been working with this mocap data in another piece of software, and I could export an Alembic for myself, and that would sort of take care of this whole take system for me. But for whatever reason, it does this by default, and I don't want it. So if you are not pre-treating your Mixamo data in another app and importing it as an Alembic file, this is how you get that take information put onto the main take. So we're going to go and I'm just going to, let's just split this pane top bottom like so. And I'm going to just change the scene view to a text port. And this is something that, that I had to look up how to do. But it's this take merge thing. We're just going to type a little command, and the format is basically this: take merge, and then we're going to force it using this -F thing here. We're going to say our destination take and our source take. So our destination take is going to be the main take, and our source take is going to be that mixamo.com take. So with that, I'm going to go over here and I'm going to type take merge like so, and I'm going to say the -F to force this to happen, because if you don't put the -F, it won't overwrite the main take. And so the destination take is main, and the source take is mixamo.com, and hit enter. And now, if I go up to the main take, you can see that that animation is on there. And what I can do now is just delete these other takes. I don't need them. So I'm going to right click on take 001 and just say delete take. And right click on this one. I could have said delete take and children, and that would have deleted both of them. So now we just have our animation on the main take. We're on the main take. I'm turning off auto takes as well. I don't need any of that anymore. We have our animation just the way we need it, but it's hidden inside the subnet. So if you dive inside the subnet, you can see that this is a bone rig of the entire skeletal structure over there. But then if you zoom out and look over to the right, there's these little icons floating off here. You can see we get our Lola geometry right here. And if we go down, we get Lola deform. This is where we've brought in Lola in her T-pose and then done some capture and then some override and etc. etc. A bone deformation, and we have our animation here. So I'm just going to throw down a null and call this Lola animation, like that. So now we can go back into our actual animation. I'm just going to turn this off. Oh, in fact, what I'm going to do before we get to that point is after the deformation, I'm going to scale it down by 100 because I believe Mixamo is in a world of centimeters and we need to be bringing it into meters. So if your parameter view isn't selected up here, just make sure you grab that from here or from the drop down. And we're going to just scale it down to in uniform by uniform scale of 0.01. Is my number lock not on? 0.01. There we go. Not the shear. One more time. 0.01. So now, yeah, roughly she's roughly a couple meters tall. That's what we're after. Okay, so now we don't really need to worry about this this subnet, but I'm going to leave it around in case obviously we need it to get our animation geo into our actual the node where we're going to be doing our work. So let's just jump in here, and I'm going to throw down an object merge. And then we're going to go into selection mode. We're going to select under object 1, under object freezes.fbx. We're going to scroll through this list until we find our Lola geo here, and then our Lola animation. Hit accept, and there she is in our scene. Great. I don't need this text port anymore, so I'm going to just close that up. And if I hit play, there she is doing her thing. Now, I don't also want this to play back super fast. I want it to play back in real time, so I'm going to hit the real time toggle down here. And there we have our dancing and our backflip, etc. And it looks like it stops at frame 160. So I'm just going to set the bounds of my animation to 160. All right. So now if I go back out here, let's turn on the room in the camera. And I'm just going to look through my camera real quick here. And just turn on my animation. And we can see that we've got our dancer framed up in the scene like so, which is good. But there's an issue. And I don't know why this is the case, but if you look at it, her feet are nicely on the ground right now, and then she goes and does a handstand, and her hands are floating above the ground, and I don't understand why. I don't know if there was a box there. When I was doing this, I tried placing a box here to see if if she was actually dancing around a box that she then jumped up onto. But there's actually, her feet were actually penetrating through that box, at least on this part right here. Her foot would have gone through that box. So I really just, I just decided to, just kind of hand keyframe her hands so that they stuck to the ground. So I'm just going to do that real quick right now. Let's throw down a transform node, and let's just go out to where her feet leave the ground, which is about right here on frame 40. I'm just going to set a keyframe and translate Y. I'm going to switch to my side view, which is, let's see, spacebar 4. Should give me a good view here. So on frame 40, I just want to kind of drop her down so that once these hands become flat, like so, she's actually on the ground. So let's just grab the manipulator and just drag this down a little bit like that. And I'm holding Alt and clicking in my Y parameter up here so that it sets a key. And then you can see that she actually kind of dips down a little bit to right here. I'm just going to bring it back up and just set a couple keyframes manually to keep her kind of on the ground. So maybe I'll bring it back down a little bit here and go forward a little bit more. And then it looks like she's up a little bit here. Do that. And maybe I'll bring it up a little bit more right here. And then at this point, her hands and her feet are touching at the same time. So I just kind of winged it. And at the point where her feet start coming back down, like about right here, I just, I'm just going to animate this up so that she's back to 0. And why? So, I mean, it looks a little weird, but I think that once we abstractify this a little bit, it won't be so obvious. It looks like there's a little dip here. Maybe I'll kind of get that one up, and maybe I'll bring this one up a little bit, and also set a keyframe there. And I'm going to call that good enough for me. So let's hit spacebar 1 to go back to our perspective viewport. And now when we go into our camera view and we look in our room, you can see we've got walls and a ceiling. We'll use these all for collisions. But we've got our dancer nices framed up and everything sticking to the ground good enough for our purposes. Moving on. Next order of business, I'm just going to put down a null that is going to be called the input animation. And here you could either wire in your test geometry, you could either wire in the crag, which I'm not sure if the camera angle is going to really work for this. You might need to adjust your room and camera accordingly. Also your frame range if you're going to be using crag, but for our example, we can just go with this sort of framing. It's going to be good. So our input animation. Now what we need to do is sort of create, we want to fill this object with spheres, and then we want to use those spheres in an RBD sim, because I think it would be really cool if after the fact on this flip, she, right here when she lands, it's going to, she's going to shatter. So we're going to combine some of the stuff that we learned in the rigid bodies section with this section, just as a little refresher, but also add just another extra layer of cool to the final product. So once we get that sim done, then what we can do after that is attach a bunch of wires to it, and it's going to look so cool to have, you know, multiple different types of physics systems happening seemingly at once, but really we can just drive that second vellum strand simulation with an underlying rigid body simulation and animation. So let's do that. Let's create the spheres for our character. So what I'm going to do to fill this character with spheres is throw down a for each loop. I'm going to say for each connected piece, and just wire this in here. And I don't want this to update every single frame. I want it to only work on the first frame. So we'll use this sort of as our binding frame, this first frame right here. So we'll set this frame up and then deform it later. So I'm going to throw down a time shift to lock this frame in place. So if I go up here to this frame and right click and say delete channels, now when I scrub the timeline, there is no animation. You can see up here we've got our animation ghosted, but right here we're just locked in. So now in our for each loop, we know that we're only going to really be working on this one frame, so it's not going to be updating and messing up our geo every single time, which is good. So next thing we want to do is create a VDB from polygons. So VDB from polygons. Now there's going to be issues because with a lot of this geometry, if we go down to the bottom here, you can see that it doesn't look like VDB was really successfully created. So if I go into single pass mode by clicking the bottom of my for each end here and going to single pass and moving through, you can see that there's issues. Looks like, well, first off, It looks like our actual dancer is still appearing, and I believe that might be an OpenGL issue. So I'm just going to go back and forth between a couple nodes to see if I can shake it loose. And if not, I'm just going to hit this plus icon here, open up a new pane tab, and open up a new scene view. You can see that this one was glitching out, and now it's no longer glitching out in this new scene view. And it looks like I might have gotten it to work over here in this scene view as well. So I'm just going to close that other scene view. Just one of those weird things that happens sometimes when working with stuff with geometry in the viewport. So now this isn't a very high res VDB, so I'm just going to crank this resolution up by bringing down this voxel size. So I'm going to use a voxel size of 0.01, and nothing is working. So let's just bypass this VDB and see what's happening. You can see that this geo of her legs that we're on right now with pass 4, and you can see it also happening with pass 3 and 2. These are all hollow geometries. So going back to pass 4 on the legs, I mean, just as an example, what we'd want to do is fill this in. So I'm just going to do it really rough because this doesn't need to be super perfect. So I'm going to throw it on a polyfill. I'm just going to wire that in right here, and you can see that it closes that geometry off. So now when we make a VDB out of it, it is pretty much exactly the way we want it. It's all closed up. So now we'll just check and make sure that that worked for everything. I'm going to untick single pass, and it looks like we've got a good old VDB of all the parts of the body, which is good. So now there's another node that we can do to turn this into spheres, which is called spheres, VDB to spheres. So throw that in there, and you can see that it creates, it tries to do its best to fill our VDB that we created right here with spheres. And this is a technique that is kind of used in rigid bodies, but we're just going to sort of, to create proxy collision geometry, but we're going to just use it for our purposes to create some interesting sphere-filled body. So values that I found that I thought were nice for this, we have a minimum radius and a minimum number of spheres and a maximum number of spheres. I wanted to basically say you can use as many spheres as you want, so I'm going to untick the maximum number of spheres, and you can see that it starts to fill in nice and dense. But I don't really want spheres that end up this large. So what I figured I would do is I would turn on this max radius and maybe dial that down a little bit. And you can see that once we get down to around, maybe around 11, we get the body filled in nicely. But also another thing is these spheres, I want to actually do a sim out of later. So, and I don't want them overlapping, and thankfully there's this awesome option right here to make them not overlap. So really they're all just sort of, you can see before they were kind of intersecting each other here, and now they're no longer intersecting. I'm going to make my background dark now by hitting the D key and go to the background and choose dark mode, and I'm going to also turn off my origin gnomon under guides here. So I've got this geo, and it looks like there's like a nice bulge on the head that doesn't bother me too much. It's kind of cool. And in fact, it is even overlapping a little bit, but I don't think it'll really matter in the end. It just looks weird, and I'm cool with it. So now that we've got all these spheres, what I want to do is just randomize their color, because I want to actually use color information later on down the road when we export this into Cinema to drive a different shader for each color. So I'm going to just do that by throwing down an attribute randomize. And I just want to randomize a grayscale value. So what I'm going to do is just create a temporary value. I don't want all these colors like this. So I'm just going to throw down a attribute I'm going to call value. You can call it whatever you want. And we're going to make it a one-dimensional. And then the next thing we can do is throw down a color node. Oops, color. And now if I wire this attribute randomize into the color, I can select a random or a ramp from attribute. So I can make a ramp, a color ramp based off of whatever attribute I want, and I'll use this value. So I'm just going to type in value here, and you can see we get a bunch of different grayscale balls. Good. So now what I want to do is actually get this geo ready for simulation. And what I can do if you remember from our previous lesson, what we have now is a bunch of different points. But what I can do is actually pack these up so that they can be used as packed primitives in a rigid body simulation. So let's do that. I'm going to throw down an assemble node and wire this in here. And I'm going to say create packed geometry. So now what we do is we've got a whole bunch of packed pieces that are all ready to go for our simulation. Now I can just point deform them. So let's bring in our let's bring down a we'll throw down a point deform so we can get our animation back onto these spheres. So point deform is like basically the holy grail of getting strange animated things to stick to figures in Houdini. In the first input, we are going to wire in the mesh that we want to deform, which is the assemble right here. And the next input wants a rest point lattice. And then the last input wants a deformed point lattice. So the rest point lattice is simply, well, if we go up here, we want the first frame of our animation to be rest. Well, we already have that because we time shifted this node to frame 1. So this first node right here can actually serve as our rest. So I'll just bring this one down here, wire it in as our rest. And then the next node, we could just use the input animation right here as the deforming point lattice. So now when I highlight this node, you can see we've got all our spheres, but they're being pulled along with our animation just the way we're after it. Cool. Now I'm seeing like a little, it looks like there's a little pop in this sphere right here, because it's probably trying to figure out what it's because this point deform has a sort of search radius, and it's probably trying to decide or average its position amongst many points that are around it. So I might bring down the number of the point count to a lower number, or I could try to decrease the radius to get that to, or increase the radius maybe to get that to stick into the right place. But it doesn't really bother me that much. It looks like it's kind of sorted out right now by just increasing that that capture radius slightly. But yeah, looking pretty good. So I'm going to leave that the way that is. And the next thing I want to do is actually run this through a rigid body simulation. What I'm going to do this time, I'm going to do something a little bit trickier, which is, it's not really tricky. It's just, you know, something that you can do. You can actually do an inline DOPNet. You know, before we normally would go out here and create like a rigid body, maybe from the shelves or whatever, and then it would create a DOPNet out here for us. But this is a pretty simple rigid body simulation, and I really am going to want to do more work in this network right after it. So just another kind of a cool trick, you can actually throw down a DOPNet right here. You can throw down a DOPNet inside SOPs, and you can actually just wire in your geometry and then have a go at DOPs right inside of here. So I'm going to throw in a rigid body solver. If I dive inside here, you know, it's just like any other node. You just jump right inside. I'm going to throw down a rigid body solver, and I'm going to throw down an RBD packed object. And the RBD packed object, under here it has a geometry source. We can choose first context geometry. That first context geometry is referring to out here in this DOPNet, this first input we have right here. So anything that's coming in here, if I go on this RBD packed object and choose first context geometry or second or third, fourth, whatever, it will pick whatever that input is coming in. And because that input coming in has a name attribute and it's all packed fragments like this, that means that the rigid body solver and the RBD packed object are going to know what to do with it. So let's wire the RBD packed object into our objects input, and then let's just create a gravity just to make sure stuff is working. So I'll wire the rigid body solver into a gravity and then into the output. And if we go back to frame 1 and click play, all the spheres fall down, which is good. And I know that right away what we're going to need is a something to collide with. And we had that room that we created before. We could just, to make sure things are working and that all these spheres are working properly, I'm just going to throw down a ground plane to start off with, and then a merge. And I'm going to merge the ground plane with the gravity node and wire them into the output. just to see and make sure that these balls or spheres are all behaving correctly, and it looks like they are. So our sim is just really kind of falling apart at this point, and there's no animation on it. So we want to do what we can to get this to animate, and then we will break it apart at our discretion later on. So let's go back out here into SOPs, and we're just going to add some attributes leading into this .NET. So I'm going to throw down an attribute create for that. And the attributes we're going to use are one we've already used in the rigid section, which is the active attribute. Active, we're going to set that to 0. And active is a integer attribute, so I'm going to set this to integer, and by default, its value is set to 0 already for us. Then the other attribute we need is the animated attribute. And this animated attribute basically is going to tell the simulation to not only leave the spheres where they were, but sort of attach them to what their incoming position is in terms of animation. So I'm going to just go over here. There's this little plus icon next to this attribute. We can just add another attribute in this on the same node here. And I'm going to set this to animated. Is the name of the attribute, and these two are just another couple of those attributes that you eventually will start to add to your list of attributes that you remember, and eventually you'll know you can just go look them up or whatever. There's tutorials out there all over the place, or you can come back here and check it out to remember how these work. Animated is also an integer attribute, and we want to set it to a value of 1. Because 1 means true. And is it animated at first? Yes, it is true. And is active? Are these points active at first? And the answer is 0 or no. So now if we watch our .NET and we're playing back, we can see that those spheres are animated properly, and it's caching them all out. So now we just got to choose a frame that we want to maybe have these parts reactivate. So now what we have to do is actually set these attributes dynamically somehow inside of our .NET. And we can do that using a simple pop-up. And if I just wire this in here to the post solve, I'm just going to dive inside and see if I can get, now we've got our dancer doing its thing, but it's still, we got to just see if we can modify those attributes right here in this pop-up, which is a great way to modify attributes. Just to see if we can get this thing back working, let's just do something super simple, which is a bind export. And we're just going to bind export to the active attribute. And use this active attribute. We're going to set it as an integer, and we're just going to overwrite it with a constant. That constant is going to also be an integer, and we're going to set it to 1. So basically we're just setting active to true. So if I come back out here and click play, you can see that the animation starts for like 1 frame, and then it stops and becomes a rigid body simulation. Perfect. So now what we want to do is maybe delay that. If I just mute this for a second and play this back, you can see that it looks like we've got this dancing happening, but I really want that to release when we've got this during this flip. And I think right as this foot is coming to the ground, I want to get that animation to release and become an active rigid body object. So what we can do is we can actually just use this activation. This activation means that this VOP is currently active. And it's not the activation of the actual pieces themselves, but rather the actual activation of the interior of this thing actually doing anything to our simulation at all. So we can, you could get tricky in here and try to use the frame number, blah, blah, blah. But what we can actually do is just go up here and set our keyframe up on our activation parameter. Now you could set this a keyframe here to true, and then go back 1 frame and select to make it false on, or just set it to 0 on frame 27. But I like to do it the script way. So I'm going to put in $F for the frame number and say the frame number is greater than 127. Basically what that says is whenever this frame is above frame 127, I want you to activate the contents of this pop VOP, which is going to then activate the active attribute. If that's not confusing. So let's just I'm just going to click on this activation to see if it's working right. So I slide to the left, activation is 0. I go to the right past 128 and it becomes active. So now if I go back to frame 0 and unbypass this and click play, see our dancers going around, doing the handstands, does the flip, and then shatters like so. Looking good. Again, flip, and then breaks apart into a bunch of pieces. Cool. First thing I'm noticing is that they aren't very bouncy or fun. So I'm going to add some bounce to the physical properties of this rigid body object. So let's go back to our camera here. Select our camera from this view and just kind of watch how things are happening right here. I think what I'll do is I'll just go and select my already packed object, go to the physical tab, scroll down a little bit here, and then on the bounce, I'm just going to crank this up to, you know, something high in the 0.9 region and just give that playback. Much more explosive and fun. Cool. Now the only other thing I need really at this point is to have it collide with the walls, because we're going to be attaching wires to our walls, and there's going to be walls in the scene at the end of the day, and we don't want any weird intersections or balls traveling through walls and stuff like that. So let's bring in a static object. The static object that we want to actually merge it with we can actually replace our ground plane, since our static object is going to be the room itself. It's going to provide a floor for us, but I'll leave the ground plane there for now, but we'll just throw down a merge. And I'm going to merge the static object and the ground plane together and then just wire that in there like so. And then I accidentally clicked the display flag, so I set the orange flag to the output at the bottom. Static object. I'm going to go and select a SOP path. So I'm going to click this picker right here. We're going to collapse the animation. We're going to go all the way up here and collapse this breakdance freezes. And then we want to select our room. And I'll select this room null and hit accept. Now, if I zoom out here, and I'm going to turn off display geometry and say under collisions, under bullet data, show guide geometry, you can see that this is our box. Our collider box. So you'd think like you go and look at your camera and we'll click play and we'll let it go out to frame 128, but all those pieces are not bouncing anymore. They're just sort of being pushed into the ground, and that's because this box is actually we're inside this box right now. It sees everything that it's doing. It's trying to actually push itself outside. The bullet solver is trying to push all those pieces outside of the box because they're inside of the box, which we don't want. And we can get around this by actually just breaking apart our box into separate planes for each of the walls. So let's do that. I'm going to go back up here. I'm going to go actually all the way up to the object level and go into our room, geo, and I'm going to throw down an edge cusp. And just to illustrate, if I grab one of these walls on the room and I just translate it like this, we're just pulling that face off. So I'm going to just delete that edit. We don't need that. But if I wire in this edge cusp and say cut boundary points, and now I go select that wall and select the move tool and move it, you see we've got a unique wall here. All the pieces have been broken apart, so to speak. So that now we can treat each one of these individual wall pieces like it's its own collider. So I'm just going to get rid of this edit, and I'll throw down a new null, and I'll call this, let's say, room cusped. So now we can go look at that. We can go look at this null in our geo, in our simulation. So let's go back to animation and dive into our DOPNet. And in here, we're actually going to select not the room null anymore, but the room cusped null, and hit accept. And now if I go down here and say create convex hull per set of connected primitives, it's not going to really change too much on the guide geometry, but it should create new, an individual collider for each one of those walls. So let's go back to our cam 1, let this play out to frame 127, and we get our bounciness back. And if we actually display the wall geometry, maybe we get a little bit of an indication as to these balls hitting these walls. Maybe if I go and look at a side view, or maybe I'll do this, since I really can't see here and I can't do an X-ray here. I'm just going to show, I'm going to just turn off display geometry, jump back out here, and our DOPNet. Yeah, if we go back out here, you can see the DOPNet is actually displaying that collision geometry. That's because it's bringing in all the objects. So really, this is kind of like almost like what a DOP import would do. DOP import actually brings in an object. It's got an object mask here, and you select a DOP network, and it basically brings that geo in. Well, this DOPNet is actually displaying all that geo. It's displaying a ground plane and everything. But we only want the RBD, the actual RBDs themselves. So the object mask we can put in here, we can actually choose to only display the RBD packed object 1. So I'm just going to copy this, jump out here to the DOPNet, and say, instead of this star, which is import everything, so I could hit paste this, and now it's only importing the RBD packed object from in there. So that's cool. And then the other thing I do is just ghost other objects. So now we can see through the wall, and we can see that these pieces, most of them are colliding with the wall. It looks like some of them escaped. Yeah, like these, a couple of these escaped. So we could probably get around that by, let's see, maybe we could do a little bit of a, we could increase the substeps. So on the rigid body solver, since this is a pretty fast simulation, maybe I'll just go to the bullet. It's got 10 substeps already. That seems pretty good. Let's just do 30 and see what happens. Go back to frame 1 and click play. In fact, in here, I could turn on display geometry and hit the W key. So it's wireframe mode. And let's let that play through. Yeah, it looks like just adding more substeps allowed all those rigids to stay inside the box. And they're colliding with the box, so good to go. Awesome. So now we're actually importing that geometry out of our DOPNet. I'm going to hide other objects and turn off wireframe mode. So now what we need to do is I would just cache this so we don't have to recalculate it all the time. Even though it runs super fast, it's just nice to have a cache. So we don't need this DOP import. I'm just going to delete that, and I'm going to throw down a file cache and wire in this. And here I will choose to, I don't like writing into the geo folder. Geo folder I like to kind of keep for input geometry. I'll create a cache folder, and I'll write it to $OS for the operator name, which I'll set in a second here. And then another file version name directory based off of hip name, and that will be our string. So it'll go into a cache folder, $OS, $hip name, based off the file name, and then another string based off of all the information, including the frame. And I just want to name this the RBD cache. And it's already set from frame 1 to 160, so I'll just hit save to disk, and it should go pretty fast. And you can see in our RBD cache folder, it's created our dancer N1 RBD. Boom. All the pieces are there. I can click load from disk and scroll back and forth, and we've got our sim looking good. So now we can kind of bring this in onto the next part, which is attaching wires to it and using it as also a collider in our next sim, which is going to be a vellum sim. So what we want to do to actually attach points to this is we want to unpack it. See how this is middle mouse click on this, it's all points and primitives. There's only 696 of each one of these because they're all packed RBD objects. And we want to turn them into actual geo so we can actually glue some stuff, constraints onto it, glue some wires to it, because in its current state it just isn't quite recognizable. So let's do a unpack node right here. I'm going to throw it on an unpack. Now you can see that if I wire this in here and middle mouse on it, it's still the same number of primitives, but we've got our new attributes back. The reason why it's the same number of primitives is because we were using primitive spheres in the first place. You know, like when we throw it on a sphere, there's this primitive mode, and that basically means that there's just one primitive, one point. It basically is sort of almost like a packed version of geometry itself. But we could throw down a convert node. This convert node will actually convert all these spheres back into polys for us. Like this. You can see now it has done a rough approximation by turning each one into this sort of, I don't know, dodecahedron looking thing or whatever. But now if I middle mouse click, you can see we've got a point count, a primitive count. This all sort of makes sense with what we think of as usual geometry. I just want to increase the resolution of these spheres a little bit. So let's go to divisions per span. And I'm going to just leave it at that. We can always subdivide it later in, I think this is good for collision geometry, and we can always subdivide it later in Cinema or wherever we're deciding to render it. We can subdivide it at render time. In the next step, what we got to do is create our wires that are going to sort of hold our character or be attached to our character here. So let's throw it on a null to just denote that this is our RBD simmed character. So let's call this our RBD simmed character. And the next thing we're going to want to do is scatter points onto this. And so the theory behind it is we're going to actually scatter points, and then we're going to project them outward into that room that we have. So let's bring in the room using an object merge. And I don't need the cusped room or anything like that. I just want the regular old room, like this. So the idea is we scatter points on this character here. Then we project those points outward from the normals facing direction of these spheres, and we project those points until they collide with this room. And for each point, we're going to give each point an ID, and it's going to have a paired ID with whichever point was projected out into this room, so that we can run through and add splines that connect them all. So to get the normal information to project away from this object, we're going to add some normals to our character. So let's do that. Because we have converted our geometry, we can now add normals. And if I look at this, you see we've got this green is denoting vertex normals. We don't want vertex normals, we want point normals, because they're going to transfer to our scattered geo. So our scattered points. So if I say add normals to points, now they get blue, and that's looking great. So now let's scatter. I'm gonna scatter. Let's do 50 points just to start off with. So I've got 50 points scattered about our character, and they all have normals that they have inherited from this normal attribute that we created here. If I turn this off, you'd see there's no normals, but now we've got normals on our scatter, so that's good. All we can do is actually ray these points out into this box. So let's throw down a ray sop. This ray sop is what we use to do this sort of projection. So now if I wire the scatter in here, and the destination, or whatever this is, collision primitives, we're going to grab our box geo over here, and I'll highlight that. You can see that all those points have been projected outwards until they hit that box. And you can see that it's doing that. The method right here is set to project rays direction from normal. We could set that to like a vector attribute, for example. If I just say delete channels here, we could actually project in a direction. So it's projecting all those points along the x-axis and it's colliding with the wall like that, or our z-axis. We could do one in that direction. It projects them all this way, but because we've got a custom vector from our normal basically for each one of those attributes, it projects all those points out to their respective like wall positions, or positions that are facing away from them at the wall, which is good. So now what we could do is you could try to throw it on an add node. And get some sort of connect polygons by group. You can see that they're just sort of all over the place. What we want to do is actually use an ID attribute to denote which particles correspond to their starting points. So what I need to do is actually add ID attributes to this scatter. So I'm going to do an attribute create. And here, we're going to create an integer attribute. I'm going to go over here, split pane, top, bottom. And I'm going to right click and show the geometry spreadsheet if yours wasn't already showing. It looks like I might have closed mine at some point. So over here, we've got our attribute we're creating. We're going to create an ID attribute, and we want to create it based off of this point number. So let's use PT num down here for our value. You can see that now our IDs, which is over here, now perfectly match up with our point number. And then when we array them, those carry through. So now I can create a group. Well, I can actually merge these together. So let's do a merge. We're going to merge these points that we're going to merge these original points that were in their original positions, which is good. And then we're going to merge them with these points that were arrayed away, and then if we throw our add down after that, and then set our add to by attribute and use our ID attribute, you can see that it creates a straight line from all of our points to their corresponding arrayed points, from the starts to the ends. I'm just going to turn off the normal view for now, because we don't really need that. I just want to template my RBD simmed character and just take a look at what happens when we play this back. You can see that these points are jumping all over the place, right? It's completely random from frame to frame, which is not what we want. The issue with this is that if you scatter onto animated geo, and I'm just going to hide this simmed character. If we just go and look at these points that we've scattered onto our geo here, I'm going to hit the D key and just increase the size of my points so that's a little bit easier to see for the recording. But it's kind of hard to see, but these points aren't sticking with our geometry. If I template our geometry, you can see that the points are actually kind of jumping all over the place, which really isn't what we want. We actually want to stick these points to our geometry, just like how we did with these spheres, just like how we stuck these spheres to our actual animation. So the way we're going to do that is later on, we're going to actually, later on we can stick these points to their positions, but we're going to need to actually pin these points to our geometry. We need them to be in one place. So to do that, we're going to do some more tricks with time shifting and with point deformation. So the first thing is, let's throw it on a time shift. And then I'm going to bring it in right after the simmed character. And I'm just going to set this to frame 1. So now all of our scattered points, the geometry isn't changing position, so it isn't reseeding every frame. We just get these points that are sort of stuck in space like that, which is good. Because we can always come back and point deform them later on. But now we've got this consistent these consistent strings for us that are set up that we can set different groups and manipulate later on down the road. But if we turn on our point display here, you can see that hit the D key and go to visualize or guides and turn up my point marker size. You can see that these points, this geometry is just 2 points, and it needs, in order for it to behave like a string, it actually needs more points that it can kind of flex around. So we need to resample these. Let's throw on a resample. And you can see here we get a whole bunch more points, which is good. I'm just going to increase the resolution a little bit by decreasing the length of that resample to 0.05. So I'm just cutting it in half from what it was. You can see there's lots of points here that we can use to simulate our strings. So now that we have these hair strands, let's just hook them up to Vellum so that we can see that things are working. So I'm just going to jump out here, and because we've already got a DOPNet that is created right here, if I start to use my shelf, this Vellum shelf, it's going to start creating objects inside of this DOPNet that we used for our rigid body sim, and I don't want to do that. So what I'm going to do instead is I'm going to create my own DOP network out here to house the Vellum sim. So I'll call this the Vellum sim right here. So now down here I can select my Vellum sim. From this, I can select this little checkbox next to the Vellum sim right here, and it will, whenever I use the shelf tool, it will apply the shelf tool's dynamic setup to this DOP network that we selected right here. So I'm going to choose Vellum hair, and I'm going to select this animation now. There's a lot going on inside this animation node, but because the last node selected was this resample node, it is what's going to be turned into a Vellum object. So if we go up here, making sure that that last resample is selected, and select our animation node and hit Vellum hair, it's going to create that Vellum setup for us in our Vellum sim DOP, which is good. And it's just adding an export node for us as well to bring that out. But in our animation, now, right after the resample, it has added these Vellum hair constraints, which is exactly what we want. We get these sort of, you can see right here, the constraint type is set to hair, and we get all sorts of stretching, thickness, stiffness, damping ratio, etc. So let's just jump into our Vellum sim and make sure that everything seems to be working properly. It doesn't look like, if I hit play, nothing happens because there's no gravity. So let's add gravity in a ground plane just to get started. So I'll throw it on a gravity force, wire that in here, and then I'll create a ground plane just to have some initial feedback on what our collisions are doing. And I'm going to turn off point display, and maybe I'll leave it on actually. It's kind of hard to see without. We click play, and all of our wires drop to the ground. Nice. And they're all behaving like hair, which is looking pretty cool. So, but it's not attached to anything. And we wanted to attach it to those pieces of our room. So let's maybe go in here and create some, like we did before. If we look back at our animation section here and look at our hair constraints, we actually have this section where we can pin to animation again. So we could create some groups and feed them in here, and it would pin those points to points on the animation. So let's do that. I think right after this resample, what we could do is kind of maybe loop through each point, select the first point, make that a group, select the last point, make that a group, and then set both of those groups to do different things and serve as our pin constraints in our network. So I'm going to loop through this geometry using a for each. So we're going to do for each, and we're going to just do for each primitive, because if we throw in our primitive numbers, you can see that there's just one primitive for each one of these points, even though, or each one of these lines, even though we've got all these points, which is cool. So we're going to just do for each primitive. And I'm going to bring these constraints progressively downward. We're actually, in order to get this whole thing to work, we're going to be throwing a whole bunch of nodes in between where we're at right now and where these constraints are finally created. That's the beauty of it all flowing through, is that we can continually refine the input to our sim and check the results. So I'm going to just wire this for each in here, and let's just maybe focus on one of these primitives at a time. So I'm just going to set it to single pass and just take a look at this first primitive we've got here. So if I turn on our point numbers, we've got points 0 to 74, it looks like, and what we want to do is create a group out of the first and the last point, put them each into their own separate group. So let's do a group by range. Group by range allows us to sort of pick a boundary based off of the point number of how many points we want to have selected for that group. So let's, I'm going to, we want the group type to be points. And I'm going to call this our starts group. So we're going to have a starts group, or maybe just, yeah, we're going to have a starts group and an ends group. So what I can do for the start group is I want the start, if I've started at point 0 and end at point 1, you can see that it actually will, we're decreasing the amount of range that we're actually selecting. So if I want my start point to actually be down here, we could start at point 1 and go to point 0. But then that's actually selecting all these points. If we invert that range, so the start points are on our character, we just invert that range and we get that first point there. So we can just get another one by adding this adding another group here, and we're going to call this one ends. And ends, we can just do sort of the same thing. I'm going to. Now, the problem with this, with doing this, is we don't get really any feedback. If I turn points on here, it doesn't look like I'm seeing any sort of feedback. So I'm going to temporarily disable the starts group so that we can just sort of observe what the ends group is doing. And we just kind of want to do the opposite. So now the ends being the things that are on the wall. Now if I modify the start, well, that's building off from here. If I increase the end, you can see that it takes 1 point away from the end here, and I can do the same thing, just invert that range. So now we have ends group and a starts group that are on either side of this primitive. And if I turn this off of single pass mode, and I'm just going to turn off all these numbers, and if I just go over here and maybe throw down a blast, and I'm going to just blast out the ends group and say delete non-selected. You can see all of our endpoints are connected to the wall here. And then if I just do the opposite of that and set this to starts, we get all the points that were initially scattered on our character. So our starts and our ends group are working properly here. So now what we can do is in the hair section here is we can set our pinpoints, and we can just select pin to animation. We can select the ends and the starts. And for right now, I'm going to just say match animation. But we don't actually have any animation on these points. If we click play, they don't do anything. But if we go into our vellum simulation and click play, the points are sticking to the wall. And they're sticking to our character. It's just that nothing is actually animated yet, but it's starting to do the thing, which is cool. So the next thing we want is to actually get this animation rolling on our character so we can get some sort of feedback with that. So the way we're going to do it is we're going to actually do it similar to how we did in the vellum examples. We're going to, I'm going to go back over here to our animation. And I'm actually going to switch over to the quad view. So I'm going to hit the Alt key on this middle area right here. That just kind of pivots these two. And then right here, I'm going to split pane top bottom. Up here, I'm going to split pane top bottom from these little triangles. Then right here, I'm going to go down here and right click on this tab and choose network view. I'm going to go up here on this tab, right click and choose parameters. I'm going to right click on this push button and choose 1 and 1, and up on this one 2 and too, like that. So now I can look at two networks at the same time while I'm messing with my stuff over here. Again, this is, I created this layout in the intro. It's called the quad layout. But in case you weren't able to follow along at that point, that's how you do it again. So now I can keep my constraints up over here. Now I can jump over to the sim and see how these things are affecting the sim. Just have them both visible at the same time.